For 50 years, the smartest scientists on Earth tried to solve one problem. How do proteins fold? It sounds simple. It's not. A single protein with 100 amino acids can fold into 10 to the power of 47 different shapes. That's more possibilities than atoms in the observable universe. No human could solve it. No computer could brute force it. And then Demis Hassabis, a chess prodigy turned AI researcher, built a system that solved it in minutes. It won the Nobel Prize. It changed medicine forever. And it might be the most important thing AI has ever done. This is the story of AlphaFold. To understand why this matters, you need to understand proteins. Proteins are the machines of life. They're not just things you eat for muscle. Every chemical reaction in your body, from digesting food to fighting viruses to reading these words, is driven by proteins. There are 200 million known proteins, and what a protein does depends entirely on its three dimensional shape. A protein that fights cancer has a different shape than one that causes cancer. If you know the shape, you can design drugs that fit it like a key in a lock. But for 50 years, determining a single protein's shape took years of painstaking lab work. X ray crystallography, cryo-electron microscopy. Each structure cost millions of dollars and took an entire PhD to solve. By 2018, humanity had solved about 170,000 protein structures total in 50 years. At that rate, it would take billions of years to map all 200 million. Enter Demis Hassabis. At age 4, he taught himself to play chess. By 13, he was the second highest rated chess player in the world for his age. He went on to build video games, earn a PhD in neuroscience, and co found DeepMind, an AI lab with a single mission: solve intelligence, then use it to solve everything else. In 2016, his team built AlphaGo, the AI that beat the world champion at the ancient board game Go, a moment experts said was decades away. During that game, something extraordinary happened. Move 37. AlphaGo played a move that no human had ever played in the 3,000-year history of the game. The commentators were stunned, the opponent was shocked, and it won the game. That was the moment Hassabis realized. AI wasn't just matching human intelligence, it was finding solutions humans had never imagined. And he decided to aim that power at the biggest unsolved problem in biology. In 2020, DeepMind entered the Caspi competition, the Olympics of protein folding prediction. Teams around the world had been competing for 25 years, slowly inching accuracy forward. AlphaFold 2 didn't inch, it leaped. It predicted protein structures with accuracy comparable to experimental methods. The organizers called it a solution to the 50-year-old problem. In the competition's history, no system had come close. But Hassabis didn't stop there. Instead of keeping the technology proprietary, he open sourced the entire thing. Every single one of the 200 million known protein structures predicted and published for free. 3 million researchers in 190 countries downloaded it. Within months, scientists around the world were using AlphaFold to develop malaria vaccines, fight antibiotic resistance, understand genetic diseases, and design new materials. What took a PhD and millions of dollars now took minutes and cost nothing. The real world impact is staggering. Drug discovery that used to take 15 years and billions of dollars is being compressed. Hassabis founded Isomorphic Labs to build an end to end AI drug discovery pipeline. They're designing molecules that bind to target proteins with precision that was impossible before. Virtual screening of millions of drug candidates happens in hours, not years. Toxicity, prediction before a molecule ever enters a human body. Beyond drugs, researchers are using AlphaFold to design enzymes that break down plastic pollution, to engineer crops that resist drought, to understand how diseases like Alzheimer's and Parkinson's work at the molecular level. A team used it to identify potential treatments for neglected tropical diseases that affect over a billion people but get almost no pharmaceutical investment because there's no profit in curing them. AI didn't just solve the protein folding problem, it democratized the solution. But there's a deeper lesson in this story. AlphaGo's move 37. When AI played a move no human had considered in 3000 years, it wasn't following rules. It wasn't copying patterns from training data. It was genuinely creative. It found a solution in a space so vast that no human mind could explore it. AlphaFold did the same thing with proteins. It didn't just memorize known structures, it learned the physics of how amino acids interact and predicted shapes that had never been seen before. Hassabis calls this the most exciting aspect of AI, its ability to explore solution spaces that are too large for human intuition. Chess has 10 to the power of 40 possible positions. Go has 10 to the power of 170. Protein folding has 10 to the power of 300. These are spaces where AI doesn't replace human thinking. It extends it into territory we literally cannot reach on our own. Hassabis is remarkably honest about what AI still can't do. Three fundamental limitations. First, continuous learning. Current AI systems are trained once and frozen. They don't learn from new experiences the way humans do. Your brain updates every second. GPT and Claude update every few months. Second, long term planning. AI can optimize for immediate goals, but struggles with plans that span months or years. A human founder builds a company with a 10-year vision. AI can help with each step, but can't hold the full picture. Third, consistency across tasks. An AI that's brilliant at code might be terrible at negotiation. Humans transfer skills naturally. AI has to be specifically trained for each domain. These aren't minor gaps. They're the difference between narrow intelligence and general intelligence. And Hassabis believes closing them is the work of the next decade. He's also blunt about the risks. As AI systems become more autonomous, making decisions, taking actions, operating in the real world, the potential for misuse grows. Dual purpose concerns. The same AI that designs life saving drugs could theoretically design harmful compounds. Government surveillance capabilities multiply with AI. Deepfakes and misinformation scale beyond human ability to detect. Hassabis argues for robust safety measures, not because AI is inherently dangerous, but because the people who deploy it might not always have good intentions. He pushes for international cooperation on AI safety, similar to how nuclear technology is governed. Not slowing down research, but making sure the guardrails exist before the systems become too powerful to control. Where does this go? Hassabis' vision is extraordinary. AI solving nuclear fusion, clean, unlimited energy. AI designing new materials that don't exist in nature. Superconductors, ultra efficient solar cells. AI mapping the human brain at the molecular level, understanding consciousness itself. AI assisting in space exploration, designing systems for environments humans can't survive in. And the foundation for all of it is what AlphaFold proved. AI can solve problems that are fundamentally beyond human capacity. Not because it's smarter than us, because it can explore spaces we physically cannot. The protein folding problem wasn't hard because humans weren't clever enough. It was hard because the solution space was too vast for any human mind. AI's superpower isn't intelligence, it's exploration. AlphaFold solved a 50-year problem, won the Nobel Prize, and gave the solution away for free. 3 million researchers, 190 countries, diseases being understood for the first time, drugs being designed that couldn't exist before. This is what AI is actually for. Not chatbots, not image generators, solving the problems that matter. Full credit to Demis Hassabis and the DeepMind team. If you want to build with AI yourself, we have guides for Claude Code, Codex CLI, and AI for Sales in the description. Subscribe. More stories like this are coming. See you in the next one.